IoT Radar, I'm meeting up with Wolfgang Kunz, and he is professor at the Technical University of Kaiserslautern in Germany. Good morning, Professor. Can I say Wolfgang?
Yes, absolutely. Good morning, Wisse.
Good morning. Good to see you. We're going to discuss security. Now, there are many interviews, of course, on security, but I'd like to discuss with you on your research subject, which is hardware security and the verification of hardware security. Now, you have to start helping me on this point because, but I understand that the increasing complexity of chip design and chip architecture requires a new approach on how security should be working. And I think that is exactly what your subject and your research is about. I hope.
Yes, absolutely. Thank you, Wisse, first of all, for having me. It's a great pleasure. Maybe since you mentioned complexity, let me first make a case for verifying hardware in general at the so-called register transfer level. I mean, probably the audience knows what RTL means, register transfer level. It's basically the level at which we describe hardware, the behavior of hardware, with quite a high level of accuracy. That means clock cycle by clock cycle, bit by bit, bit vector by bit vector, just like we will also later implement it in the chip. And that's the reason why these RTL descriptions are usually the golden models in our design flows. That even holds when we have high-level synthesis. Golden model means that they are the point of reference for sign-off verification before we tape out a chip. Now, on the other hand, if you have this high level of accuracy, then of course you also have complexity. But especially now when it comes to the topic of security, it's quite important to look specifically at the RTL and not only at higher level of abstractions. Just think about these famous or infamous attacks called Spectre and Meltdown. I think we have all heard about them. They are timing side channels at the microarchitectural level. And that means you only understand what's really going on there if you analyze designs clock cycle by clock cycle. And that means you need to look at these complex RTL descriptions.
Now,
and that's actually,
yeah. Now, you're actually diving really deep into the architecture of a chip, because we're now looking at registered level, flip-flops, I must say, or whatever it is, clock cycles, up and down, etc. That is like, diving to the deepest part of the ocean, in my opinion. Is that true? Is that doable?
It is a challenge, of course. Maybe it's not the deepest part of the ocean. You could also go even lower. You could go to physical layers, transistor layer, and so on. That's also interesting with respect to security, but that's not quite what we are doing. We are looking at these micro-architectural things. But yes, you're right. It's definitely deep. I mean, you mentioned latches and flip-flops. We have thousands, hundreds of thousands, millions of them in our designs. And that means the state space that we need to explore in order to detect security weaknesses, they are 2 to the million of state bits. Yeah? So that's huge. Yeah? But it turns out that formal methods have become quite capable. And if you formulate things right, and I will talk about it maybe later, you can do these things. I mean, the main challenge here, which comes on top is that we need to detect so-called side channels. Yeah? And as the name already suggests, they are orthogonal to the usual functional behavior. They are by definition not detectable by the usual functional verification techniques. So this means we really need a new class of EDA tools, electronic design automation tools, new verification tools to detect these things. Yeah? And that's actually what we are trying to do. We are trying to create a unified approach which targets violations of security targets by any hardware weakness at the microarchitectural level. It can be side channels. It can also be classical design bugs. They can also be very difficult to find. Yeah. And then, of course, we need to put everything into a setting, into a practical setting, hopefully without demanding anyone to learn special languages. There should be no special new operating systems, all these things we don't want. And in particular, we want our tools to be usable in such a way that the user doesn't have to be an expert in security.
Okay. Now, there are, of course, hardware solutions for security, memory level, encryption technologies, etc. Are they not sufficient, or what is their weakness? What is the weakness of the existing hardware securities?
I think, yes, you're right. A lot has happened in recent years to also improve security of hardware. And yet, as you also know, and that's probably one of the reasons why we have this interview, security breaches in hardware, they have been emerging at an alarming rate in recent years. And now we need to still be fair and say that many of these reports that we hear, they actually go on the account of software, while at least in the past, the processor hardware was considered performant and also a solid root of trust for the rest of the system. And I just mentioned these Spectre and Meltdown attacks. They changed the picture quite drastically, because even if you do all these advanced features, they can be undermined by these new kinds of side channels that people have detected. Spectre Meltdown, I just mentioned, there are also others. They have been detected first in Intel processors, then later also in open source RISC-V processors. And that's really the problem. It's also other types of side channels, such as classical cache-based side channels that pose a threat. And we understand that better today, after some years of research in hardware security, mostly triggered by these Spectre Meltdown attacks, than we did some years ago. And maybe if I want to mention a new topic, and that shows how quickly our efforts to put all these defense mechanisms into a design can be in vain. For example, quite a hot topic at the moment is a software paradigm called data oblivious computing. Yeah, so people try to develop software in a specific way so that we have a high level of security. Data obliviousness, that's a paradigm which essentially enforces that runtime, resource usage, and memory access patterns of a program are independent of confidential data. And that's actually quite effective. But it turns out, Pac-Man attack just reported recently, it turns out that certain hardware features, and that's something we just learned to understand, can undermine all these efforts. And then all these interesting paradigms at the software level are actually quite in vain.
Yeah.
On the other hand, if you allow me that comment as well, I don't want to sound too alarmist. We have so many alarms these days.
Oh, well, yeah.
Of course, we should also say that that not all these weaknesses that get reported and that we detect are so easily exploitable in a real world setting by a real attacker. Mm-hmm. The problem is with that we simply don't know what can be exploited easily. It's difficult to predict that, to make an assessment on that. So therefore, our goal is to detect as many of these weaknesses as possible so that we have a basis for such an assessment.
Now, one of the things you mentioned in your document, in your research document, is called Bupec, which is a unique program executional checking. That is, I understood the focus of what you're trying to achieve with Bupec. You're actually trying to promote this new approach on security. And now this is all in research, and you're pushing it out, of course, in the community of your colleagues. What is Bupec exactly? Is it already what you described, or is it just the name of it, or is it will it be more?
Yeah, let me explain.
What is the purpose of Bupec?
Yeah, let me explain a little bit. I don't want to get too technical on these formal methods, but maybe it's a good idea to start looking at how people are doing things today, because we believe our approach is quite different from that. So, for example, today in current practices, if you want to have a secure design, what you do is you first implement your design and possibly augment it, as you mentioned earlier, by some advanced security features, trusted execution environments, whatever, you just mentioned it. And then, you usually also extend your specification, covering these additional defense mechanisms by some additional functional spec, so that later when you subject everything to verification, you match your functional verification against this spec. And we believe, of course, this approach works, that's current practice, but we believe that it's quite insufficient in some cases. And that's why we are trying to do things in a different way. So what is different in HiPEAC, and I'll explain the name in a minute, is that we try to start directly from the high-level security requirements. So for example, we look at the requirement that protected data in memory can never be seen, read, stolen by a user-level process, which could be an attacker. That security-critical operations in a trusted part of the system can never be influenced by an untrusted third-party IP. That's high-level security requirements. Mm-hmm. And now what we try to do is, instead of translating them into a functional spec for some defense mechanism, which is a problem, which is difficult, you can easily miss things, we formalize these abstract requirements immediately using standard languages like system Verilog assertions, and then run these in our verification method. Now, the problem is, of course, that this leads to very global properties that we need to apply to our design. So, for example, in HiPEAC, this usually boils down to, let's say, some global non-interference property, which states that secret information under no circumstance whatsoever can influence the execution of any user-level program. So this is why we call it HiPEAC. Yeah? The program executes uniquely with respect to secret information. The point is that user programs, which could be attackers, should never be able to trigger the system, which has some secret data, of course, that it can access, to trigger the system to influence its own user-level process by this confidential data, so that some variations can be observed and some information can be stolen. And now, of course, the problem is how we handle the complexity. We have some special methods for that. We formulate this mostly like an occurrence checking problem. That means, for example, if you look at a, let's say, division unit, we do not try to show that it performs correct divisions. Other people can do that. But essentially, we try to show that it doesn't make a difference, or that secret information cannot make a difference in how a user-level program executes on this division. And only checking a difference is actually much simpler than really doing a full-fledged functional verification.
Okay. Now, this HiPEAC, this approach, verification approach, is you mentioned, of course, the problems we had in the past with Intel processors. You mentioned RISC-V. Is it, HiPEAC is generic. It works with all different architectures, I understand. So from a designer perspective, if you are doing RISC-V or whatever, this approach or this implementation, as I understand it, will most likely prevent you from side channel effects at some point.
Yes. Basically, we are looking at any ISA. We have mostly been working on RISC-V ISAs, but we believe that actually the instruction set architecture itself is usually not the key point in the whole problem. So we don't have reason to believe that the ISA is the source of the problem. So I don't believe, you mentioned Intel, that the problem comes from the fact that Intel has a special ISA, which is particularly vulnerable. We don't believe that. So our approach has this exhaustive nature, covering all side channels, vulnerabilities of a certain class. And what we found is, and I think that's not so surprising to some, at least, that the main origin of all these weaknesses is a different one. Maybe I can give you an example. Let's say we have a student here at our university, undergraduate student, and we now ask the student to, let's say the student has finished his first course in computer architecture, and we now ask the student to do a class project to design a RISC processor. We give the student a couple of weeks. Now, let's say the student has done a good job, the processor passes all the usual tests. Now, what do you think? Will this processor be on the secure side, or will this processor be on the insecure side, the processor the student has developed? The answer may be a little bit surprising. It will be on the secure side. Why? Because it's very simple. And that's actually something we learned in all these experiments that we did, and also the community has learned that.
Yeah.
That is actually optimizations that people do, certain high-end features that people do, which cause the problems. Yeah. So take, for example, classical side channels, known for a long time, flush and reload and so on. They're always based on some shared resource like a cache or, let's say, a functional unit. Yeah. If you don't do these optimizations, if you don't share functional units, if you don't even have a cache like the student probably wouldn't have, then you don't have any of these problems. Yeah. So
it's really interesting. You're a very positive man about security. I have more people, of course, and it's interesting to see that you have a very positive approach. But in your opinion, if you're looking at taking a timestamp now and taking it perhaps look further in the future, are you confident that we will get to a place where we can say, okay, this is 100% secure hardware? Can we get to that point, or will there always be something new happening which is unexpected?
Well, maybe I sounded too optimistic. Maybe I'm semi-optimistic. Yeah? Basically, if you draw the conclusions from what I just said, it means we should use very simple processes and we don't have these problems. But of course, we cannot so easily give up all the performance that we get with these advanced features and all these optimizations. So then, of course, the question is very valid. I mean, since we probably don't want to give up and just want to use third semester student processes, do we have a chance to reach 100% secure processes? Well, of course, 100% certainty, that's only something that exists in pure mathematics. Of course, the obvious answer is no, it will not be 100% secure. But of course, we do have some hopes and we do have some visions. I mean, what I do think is that we will be able, and that's my optimism, to build much more secure hardware in the future than we currently have. It's essentially a matter of risk assessment, of costs, who is ready to pay for these costs. We see tremendous progress in the research community. We both met in the context of the HiPEAC conference, and we had this interesting workshop on hardware security there, where a lot of good ideas were floating around, both to detect these weaknesses as well as to fix them. So yes, I'm quite confident there's a lot of things we can do. And now if we talk about priorities, I think what we should do first, and what would be my main point, is to first fix those things in the hardware that we cannot easily fix in the software. And quite often that means we do not even see them in the software. They're completely invisible at the level of the instruction set architecture. That's what made Spectra and Meltdown so famous. And there are estimates that we can fix these issues with a performance penalty of about 20%. Now, the problem is these 20% estimates, they are of course good, but they have been done on high-level models, and nobody has really implemented it yet at the RTL. And I mentioned earlier why it's so important to do things at the RTL. So we are working on that. So I'm somewhat optimistic we can have something close to these numbers. So summing it up, what I think is what we should do is, at first, we should fix those things in the hardware which are not fixable at the software level, which we don't see there. And if we manage that, then of course we still have the responsibility for the software people to do their job and secure the system at the software level. But at least we then have a separation of concerns. And that would be quite some progress. It would essentially rehabilitate hardware. It would rehabilitate the processor as a root of trust for the rest of the system. And that is sort of my hope, that this is a realistic perspective for the next years.
Well, that sounds great. I must thank you for this deep dive in hardware security. It's we're not at the bottom of the ocean yet, but I think this is deep enough for me.
I hope you don't discover new oceans.
Yeah, sure, excellent. Well, thank you very much for this interview. I hope people watching this will have the trigger. Okay, let's see what it is. Let's see what it is. Become part of this community of people looking at security and working on it and to make more secure hardware. So I have to thank you very much.
Thank you. It was really a pleasure.